Our next speaker is Yuan from Stony Brook, who will tell us about discounting by family Floer theory.
Okay, thank you for the invitation. So the title of my talk is Disk Counting via Family Flow Theory. So let me first briefly introduce the background of this theory. So first, this is the family flow theory was first initiated by Kenji Fukaya in around 2001. So roughly speaking, it studies flow homology for families of Lagrangian submanifolds. So we are particularly interested in this theory applied to SYZ picture. So suppose we have some nice Lagrangian fibration, and we have a Lagrangian section, and the fibers of the torus fibers gives you a natural family of Lagrangian submanifolds. And the idea is that if we consider the flow cohomology for all these Lagrangian fibers in the same time, and this is supposed to give us a coherent shape on the mirror space. And this should give us something called family flow functor. And recently, Mohammad Abuzaid used this idea to prove the homological mirror symmetry without corrections. And a natural question to ask is, so here we don't consider any quantum corrections. So we would like to ask, what if we include quantum or incident corrections? And more specifically, this is related to a conjecture by Daniel Auroux. So suppose we have a Kähler manifold, we have an anti-canonical divisor, and we have a holomorphic volume form on the complement of the divisor. Then a mirror space is supposed to be the moduli space of a special Lagrangian tori equipped with flat U1 connections. And moreover, we have a globally defined superpotential function given by FO's M0 obstruction to flow homology. So what I did in my, I'm sorry. So if you have some torus fiber L, and it's a dual fiber, it's expected to be the space of flat U1 connections. So namely the first cohomology group with coefficient in U1. So what I did in my thesis is to give a positive answer of this conjecture, but in a non-Archimedean setting. So here is the main theorem, what I call non-Archimedean SYZ mirror construction. So let X0 be some open domain in X. And suppose we have a reasonable smooth Lagrangian torus fibration. Here, I don't want to say too much about the condition on the Lagrangian fibration, but you just keep in mind that this class of Lagrangian fibration include special Lagrangian fibration. Then under this condition, we can naturally construct a rigid analytic space over the navical field, a global superpotential, and a dual fibration, unique up to isomorphism. And such that for every base point Q, the dual fiber is just set theoretically the first cohomology group with coefficient in U lambda. So as you see, the dual fiber is now using the coefficient U lambda instead of U1. And what is U lambda? So U lambda consists of all norm 1 element in the navical field. So it is very similar to the U1, so in C. And that's why I would like to call U lambda to the N a non-Archimedean torus. And then as a set, the mirror space X check is just the union of all these non-Archimedean torus. But of course, you will have some extra rigid analytic space structure. And this structure comes from the work-causing phenomenon and the quantum corrections. But today, I don't want to say too much about the proof of this theorem, and I would like to focus on examples and applications. So you have, so far you have two very natural examples, toric fibration or grossest fibration. And today I want to focus on grossest fibration, and I want to give some application for disk counting. Okay, so let me first give you some idea of this non-Archimedean SYZ mirror construction. So the rigid analytic space structure on X is locally modeled on the following non-Archimedean torus fibration. So this is a map defined in this way. Here, VAL stands for the natural valuation map on the navical field. And this is an analog of the logarithm function. So in other words, the mirror analytic space X check satisfies the following property. So if you have some small domain in the base, then the dual fibration over this small domain is just this non-Archimedean torus fibration restricted over this small domain. So here you should think this small domain as a subset of an Rn up to GLNZ transformation, because we have a natural integral affine structure on the base manifold because of the Arnold-Lewis theorem. And then you see the fiber of this non-Archimedean torus fibration over the zero is just the non-Archimedean torus, which I mentioned before. And if you take another fiber over some point C, it's just described as follows. And the two fibers can be connected by a very simple map. So here T is a formal variable in the navical field. Okay, and in our setting, let me recall that the mirror space, as I said, is just the union of all these non-Archimedean torus. And so let me pick 2 points in the base. So the two fibers are two copies of the non-Archimedean torus. And you can think of the first as a first cohomology group of L with coefficient U lambda and the similar for the other fiber. And then there will be some gluing map connect the two fibers, the two dual fibers. And the point is, if you use some rigid analytic geometry, the point is the gluing map takes this form. You have some additional term. So you can compare with the previous simple map here. You have some additional exponential term here. So a gluing map for the mirror mainly have two situations. So you may cross the wall or not across the wall. So if you cross the wall, then the two fibers are just identified with the simple map as before. So this is just like identify two fibers of the non-Archimedean torus fibration. But if you cross the wall, you may have some additional term which accounts for the quantum corrections. And I would like to emphasize that this term is only determined by the count of Maslov index 0 disk. And let me also note that knowing this pattern of the gluing map is very important for the application we discuss later. And the proof of this requires a careful study of non-Archimedean analysis. Now we have described the local picture of the mirror space, and now we can describe the local expressions of the globally defined superpotential, W check. So locally, it's just defined by the open Gaussian invariant. So here M beta stands for the count of holomorphic disk in class beta, and the mu beta is the Maslov index. So by the main theorem I mentioned in the beginning, the gluing maps also must match various local expressions of the superpotential. So you may have two situations. So if you don't cross the wall, the two local superpotentials are connected by a simple map. But if you cross the wall, the two superpotential are connected by a more complicated map. And from the first case, it agrees with the well-known fact that the open Grom-Witten invariant keeps constant along a Lagrangian isotopy, which does not involve any Maslov index 0 disk. And so it is natural to ask, what can we obtain from a gluing map across the wall? And that gives us some applications, which I want to discuss now. So here is the application. I want to particularly consider the grossest fibration on C2. So it is explicitly written in this form. And you can also visualize the grossest fibers from this map. So basically here you have two parameters, lambda and R. And the lambda is roughly the height of the torus, and R is the radius of the torus, the radius of the circle. So if R is greater than epsilon, it is called a Clifford type, and if R is less than epsilon, it is called a Chekanov-type. And I'm also interested in such two holomorphic disks, and I denoted by gamma and beta hat, and the Maslov index of them are 2 and 0. So this is the base of the grossest fibration. And yeah, so the base is separated by some wall into two chambers. And you have a singular fiber here, which corresponds to this pinched sphere. Okay, and the next I want to consider the workhorse phenomenon. So suppose we have a Lagrangian isotopy starting from a Clifford torus and end up with a Chekanov torus. Then so for Clifford torus, you have beta 1, beta 2, which correspond to the toric disk. And sorry. And if you go along the Lagrangian isotopy, beta 1 splits into gamma and beta hat. And the beta 2 just goes to beta hat. Because so the Lagrangian isotopy actually gives you a isomorphism, a natural isomorphism between the relative homotopy group. And I want to slightly abuse the notation and write beta 1 is equal to beta hat plus gamma, and beta 2 is beta hat. So it's kind of natural from the picture. Then, so you have two superpotentials. They are actually very well known. So let me skip that. And according to the non-Archimedean SYZ mirror construction, you have some gluing map which takes this form, and this gluing map must send the Clifford superpotential to the Chekanov superpotential. Okay. And in the next, we want to compactify C2 to CP2. Then, as you see, there will be some new holomorphic disk. And accordingly, the superpotentials will also change. You will have some additional terms after we compactify it. And for the Clifford superpotential, it is easy to know what is the additional term because of the work of Cho. But it is not very straightforward to see what is the additional term for the Chekanov superpotential. And here is the observation. When we compactify C2 to CP2, there will be no new Maslov index 0 holomorphic disk. However, we also know the gluing map is only determined by the count of Maslov index 0 disk. So the gluing map is the same, but the superpotentials are changed. Okay, so for the same gluing map, we have two relations with different superpotentials. And for the first, so from the first identity, we can explicitly determine the gluing map. It takes this form. And from the second equation, from the second identity, then we can compute the superpotentials. And it turns out the superpotential, so I just I just present the computations, outcome of the computation. And if you take the coefficient of all these monomials, you get the open Gomvitan invariant, 1, 1, 1, 2. And this exactly agrees with the work of Chekanov-Schlenk, but our method do not explicitly find the holomorphic disk. And this idea can be also applied to higher dimensions. So let me take a Chekanov-type Lagrangian torus in CPn. And we can compute all the non-trivial open Gomvitan invariants. Indeed, we can compute its superpotential. So let me first introduce some notation. So we have Maslov 0 classes, and we take gamma to be the sum of all these Maslov 0 classes. And then the superpotential. So by using the same idea, we find the superpotential takes this form. It looks very complicated, but it is very interesting to compare my computation with the recent Pascaleff-Tonkonog's work. So I copied their theorem here. So their work is definitely more general, but if you take k equal to n here, then we see that the superpotential is given by this, and you can compare the two superpotentials. They are basically the same. And you can take this change of a variable here. But of course, there are some differences. My computation is over the navical field, and their computation should be over C. But we get almost the same result using very different methods. And there should be also some further examples. So first I started C2 and compactified to CP2. And we can also do with CN and CPn. And actually we can also use the idea to CPr CPn minus R. And hopefully we can also do any projective toric compactification of CN. And on the other hand, we may also generalize this CN here. So perhaps we can also work with tori Calabi-Yau, following the work of Chen-Lao-Liu or Auroux-Kazakov. So we also have some Gaussian fibration and Clifford tori and Chekanov tori. And finally, I want to remark that our method seems very different from Pascaleff-Tonkonog's work. And I believe there should be some interesting to explore. And that's the end of my talk. Thank you.
Thank you very much. Questions? Maybe I'll start with one. You get those relations between the potentials for the Chekanov and the Clifford, can you also say something about Viana's exotic tori?
Viana? I'm sorry, can you speak again?
Yes, Renato Viana has those work on tori that are, there should be different from either, basically. And the question is there anything of substance in asking?
Yeah, maybe I didn't think about that.
I mean, I don't know, maybe it just...
I think the answer is yes, because as Pascaleff and Tonkonog showed, the wall crossing formula see that they distinguish all the Viana tori. So since the speaker can see the wall crossing formula, he must be able to see it.
I see. More questions? Okay. If there are no further questions, maybe we should thank the speaker again.